Hello, good morning all. In the previous lecture, we were discussing a little bit about the introductory quantum mechanics, that is the wave mechanics we were discussing. Today also we are going to continue with the same. Let us start our lecture without wasting further time. So in the previous lecture, we had actually done till something like expectation value, right? So we were discussing wave mechanics. Just let me take another pen. So, so we were discussing wave mechanics, and in particular, we have completed portion till I think we were doing wave mechanics, and in this we have come up till the rationale behind the expectation value. Okay, so why do we take expectation value? What is actually the expectation value? Till this particular point, we have done a little bit amount of physics till now. Okay, so let me reconstruct whatever I was telling in the previous lectures itself, and okay, so let me write expectation values. So till now, we have seen that a particle, the state of particle is represented by a mathematical entity called as a wave function. Or wave function. Okay, so I represent it using this. So this is how your particle is represented. And we know that psi mod whole square d tau in space anywhere from minus infinite to plus infinite, or you can take it in one dimension, let's say dx, or if you want to take in the entire space, that is from psi mod whole square d tau over in all space. Both of these quantity come out to be zero. And what does this quantity represent? This quantity, that is psi mod whole square. This particular quantity, psi mod whole square, represents what? It represents the probability density. It represents probability density of finding the particle here somewhere in the space. And if you take this particular scenario, let's say if I'm talking about x, so let us say that the psi is a function of x and t, then it represents what? Psi mod whole square represents this particular entity, that is psi mod whole square, referring to this entire entity represents the probability density of finding the particle at point x and t. Okay, at time t and at point x. Okay, so another thing that we did in the previous sections also, that what we can say that there is something called as a normalization constant. There's something called as the normalization constant that we usually find. So let us say if I have a if I say that psi x comma t satisfies my Schrodinger's equation, satisfies the Schrodinger equation, that is Schrodinger's equation, that is iota h cat del psi upon del t equals to minus h cat square upon twice m, and then you have this del square psi upon del x square plus b psi. Then you can say that a times psi x comma t is also a solution for the same. Is also a solution. Okay, if psi is a solution, then a times psi is also solution. This A is called as a normalization constant. This is something that we have done already. Okay, this A is called as the normalization constant. So I'm writing it here. This A is called as the normalization constant. This A is called as the normalization constant. How do we extract this normalization constant? So let us take one example, try to do that, and then we'll be able to understand how to find it. Okay. One more thing that we did a little bit of, if you remember, that we tried to find that if I normalize my wave function at t equal to 0, then does it remain normalized? Does it remain normalized even after some time, let's say t equals to tau? So answer is indeed yes. And we did it using a careful proof, and we actually tried to establish this particular thing that that particularly one thing that we tried to establish was that even as, so I'll write it here, even as the psi evolves in time, even as psi evolves as time goes on, A does not depend as a function of t. Okay, rather it remains constant all this while. Okay, so it happens so that Schrodinger equation automatically preserves the normalization of the wave function, the normalization of the wave function. So how do we normalize it? How do we normalize a wave function? So we normalize a wave function by this methodology. That is, let's say we have this normalization constant A. I have this psi x comma t. What do? I multiply this A with psi x comma t, try to multiply it with its conjugate, integrated, answer should come out as 1. And from here, you know that you will find this A mod whole square, and from there you can find this A. So basically, what happens is we actually did it in the previous lecture also, that we actually tried to differentiate psi mod whole square dx minus infinite to plus infinite, and we found out that this is equals to 0. Since this is equals to 0, it implies what? It implies what? That this integral that is minus infinite to plus infinite psi mod whole square dx remains constant. This is something that we have done in the previous section. I'll urge you to go through all these lectures in previously we have done. We found that minus infinity to plus infinity psi mod whole square dx remains constant. And since it remains constant, so clearly your A would also remain constant. So in general, I can say that A would not change with time. What is after all A? A mod whole square would come out, and this particular thing I have proven that integral minus infinite to plus infinite psi mod whole square remains constant. So what is this? This is nothing but it is A mod whole square minus infinite to plus infinite. You can take it as psi mod whole square dx equals to 1. If this remains constant with time, A mod whole square will remain constant with respect to time. A would not change with respect to time. So therefore, if you normalize your wave function at t equal to 0, so I'll write it here. It implies what? If you normalize your wave function at time t equal to 0, then it remains normalized for all future times. For all future times. So this is how you do, this is how you write things up. Okay. So this is one thing that one must remember. Okay. Another thing that I actually did it for you, that what is the need of expectation value and what are actually the expectation values. Okay. So just a revision of that also. And see, measurement in quantum mechanics, it's itself a itself a difficult kind of itself a feature which actually differentiate it from the classical mechanics. Okay, so in classical mechanics, while you can have a deterministic position, deterministic momentum, here the position and momentum are bound by something called as uncertainty principle, and therefore you cannot simultaneously accurately measure both x and t together. However, the entire framework of classical mechanics works on the phase space, where there is a sense of determinism when it comes to the measurement of x and t. That is the moment, that is the position and momentum. However, in quantum mechanics, this does not seems to be the case. So what happens is that we define something called as the expectation values. Okay, we define something called as the expectation values. So let's say, why I told you initially also there is a rationale behind it. And what is that rationale? Let's say whenever we talk of a particle in the quantum mechanics, we will actually not worry about a particle, rather we will worry about its wave function representation. So we'll worry about the wave function representation, which will obey some probability density psi mod whole square. This particular psi would obey some probability density, that is psi mod whole square. Now what happens is, let us say that what does the area under the graph of psi mod whole square and x represent? It would represent the probability of finding the particle somewhere. So this is from Griffith, so I'll not make any difference. Okay, so this is how he says that if I have to find the particle between A and B, this is the probability that I can find my particle in this particular region, given by integration A to B. This is psi mod whole square, and let's say this is x, and this will give you the probability of finding the particle between A and B. This particular integral will give you the probability of finding the particle between A and B. Okay, so what will happen? You can see that the maximum probability would be corresponding to this peak position, right? So you can so you can say that what is the maximum probability of finding the particle? Maximum probability would be around this, where you have this peak position. Okay, so in general, we can say that this statistical interpretation, that is sometimes referred to as Born interpretation, the statistical interpretation, what you can say, statistical interpretation of wave function, that is the Born interpretation. At times it is referred to as Born interpretation. What does it do? It induces a certain sense of indeterminacy. It induces indeterminacy. Okay, and all the quantum mechanical results, you can say all the quantum mechanical measurements, or you can say all the quantum mechanical results can be said probabilistic. Can be said only probabilistic. So if I measure something, let's say if I measure, and another thing is, in quantum mechanics, all the classical observables. This is something that we are going to see in linear algebra also. The lectures that we have right now suspended, and we are going to continue it further. And I'll take this linear algebra into a topic called as mathematical foundations of quantum mechanics. So we'll see it, but right now accept it as a postulate. So all the classical, you can say, observables are represented as operators in quantum mechanics, are represented as operators in quantum mechanics. So just give me a minute. Operators in quantum mechanics. Okay, so what happens is that since we know that the mathematical representation of particle is a wave function, and it is governed by a probability density psi mod whole square. Okay, psi mod whole square. So you cannot accurately say, let's say, if I want to measure the position. Let's say this is how it is made. Okay, if I want to measure a position, so what will happen after one measurement? Let's say my particle is somewhere here. So this particular wave function would collapse to this particular wave function. Let's say my particle is here. So it will collapse to this particular state. Okay, this will collapse to this particular state. Now, if I make a next measurement very quickly, such that the wave function does not evolve, then I will be at exactly this position, exactly at this position. Okay, so I have written it previously also. So see, if this is how your psi mod whole square is represented, and immediately after one measurement, we can find that particle is here. So it will lead to a spiky behavior, because if I am saying it is here, it implies that entire probability mod whole square d tau should give me this particular area, right? After all, psi mod whole square represents what? Psi mod whole square represents the probability density. Now you can find particle anywhere from, let's say, from here to here, if I'm saying. So I can find particle from here to here anywhere. Now, after one measurement, it would be somewhere, right? Let's say it is at this particular point. So what happens is this entire wave function collapses to this particular spike, isn't it? And this particular area would represent the probability of finding the particle at this particular point, exactly at this particular point. So prior to the measurement, I will write it here. Prior to the measurement, we cannot say with certainty, or you can say we cannot ascertain precise position of the particle. However, after the measurement has been taken, as you can see, this wave function collapses to this particular spike, and this particular spike will also be governed with some probability. Okay, so a measurement would yield a result again governed by some probability. Again governed by some probability. Okay, so now if I make a second measurement very quickly, okay, such that psi mod whole square is not evolving, I will again get this C. But understand that this psi mod whole square evolves with time. This psi mod whole square evolves with time. So let's say how to what is the way ahead? So I would write the way ahead is to find the average value. So I write the way ahead is to write the average value. So in quantum mechanics, most often you're going to see we are interested in something called as expectation value, right? We are interested in something called as expectation value or the average value. So what do we do? So let us again take one example. Let us try what we do. We actually resort to something called as expectation value. We do something called as expectation value. And what is the rationale? I told you the rationale is that we don't know the before prior to measurement where is the particle. After the measurement, particle collapses. After the measurement, the wave function collapses to a spike. Now we don't know that second measurement if I make it very quickly, then it will be there only. It will be there only. So basically, how to means how to circumvent this particular scenario. In order to circumvent this particular scenario, we do something. Let's say if I want to measure position. So what I'll do, I'll resort to the expectation value of x. Expectation value of x is given by minus infinite to plus infinite x times psi mod whole square d tau dx, sorry, or you can say this is equals to minus infinite to plus infinite psi star x and psi star dx. This is writing the expectation value of x. Now, what does this physically represent? Just give me a minute. Expectation value of position. Okay, so let us understand by a little bit of I'll make a diagram for you. So let's say I have a large sample of electrons. I have a large sample of electrons. So let's say I have a large sample of electrons. And let us say all of them are prepared in the same wave function. All of them are prepared in the same, you can say wave function or same state. So let's say all of them are prepared in the same state. But if we make a position measurement, if I make a position measurement, I will get different result. I will get different result. Okay, I will get different results. Okay, so I will get different results. And why different result? Because understand, if they are prepared in the same state, but psi mod whole square would represent the probability density. So basically, what you can say that different position measurements you can make. So you can say that all these position measurement that I'm making, they're going to follow. So distribution of these position measurements. I'm saying distribution of these position measurements are bound to follow a probability density, that is psi mod whole square. Okay, so basically what is psi mod whole square? It represents the probability density. And what is psi mod whole square theta? It is going to represent me, let's say if I'm making simply Gaussian, this particular area is going to represent me what? Probability of finding particles somewhere in the space. Okay, so obviously probability is maximum here, and then somewhere it is less. So I don't know exactly. So what I do in order to circumvent this particular scenario, as I told, I take something called as expectation value. I do something called as the expectation value, represented by this and given by this integer. Okay, now there are a little bit of lapses that one may have in thinking. So let me correct those lapses before you go on the wrong path. So eventually, first understand what does this particular thing represent. So x into psi mod whole square dx, which I refer to as the expectation value of x. What does it represent? So one gets confused, and so basically what happens is that, let's say if I am measuring let's say if I made the first measurement, the entire wave function collapses to a certain point, because there would be some probability of finding somewhere in the space. So this entire wave function collapses to this particular point. There is no sense of making measurement time and again over this, because if I make measurement time and again, I'm going to get this result only. So it does not mean, I'm writing, it does not mean, this is something that I've clarified in the previous lectures also. It does not mean measuring, measuring the position of particle over and over again. Position of particle over and over again. So what I'm trying to say is, let us say if this is what I meant, let's say if I meant the position of particle over and over again, so what will happen? Let's say after first measurement, the particle collapses to this particular state. Let's say your particle is here. So if it is here, so this particular wave function collapses to a narrower spike. Now, if you make subsequent measurement very quickly, measurements very quickly, because you also understand that psi mod whole square will evolve with respect to time also. But if I make it very quickly, I'm going to get the same result. Okay, and I do understand that probability of finding the particle anywhere in the space is governed by this. So what is then this expectation value? So I'll write it here. This expectation value of x, I'm writing right now. I'm helping you out with this position thing only. What does it? It is nothing but it is average of measurements performed on the particle prepared in the same wave function, in the same state, let's say. So what, let's say I told you, if I am having, let's say, identical electrons here, each position measurement will give you a different result. Probably it can give you the same result also, but I can expect different result because all these results are governed by this density psi mod whole square. So what is the A hat? I will try to take an average of all these results, all these measurements, and that particular average is called as the this particular thing, which is called as the expectation value. So what I have done, I have prepared, what we do actually, we prepare an ensemble. This is a technical word I'm writing. We prepare an ensemble such that each, let's say here, electron I told, is in the same wave function or in the same wave function, or you can say state. And then you measure the positions. You get some results, and those results are averaged. This is something called as your expectation value. This is something called as the expectation value. Okay, so I'm writing it here. So please don't confuse yourself with this thing. So it is not what I will write. I'll write it in notes so that you never get confused with this particular concept. Again, I have taught you, this is, I think, second time I'm teaching you, so that I'm time and again focusing on this. So this is not same as repeatedly measuring this, repeatedly measuring the position of one electron. Rather, what we are doing, rather it is equal to averaged value of repeated measurements you can say on an ensemble of identically prepared system. Please focus on this particular scenario. I think this will be this is something that you should understand. This is something that you should understand. Now, let us understand what is, I'll write it here. So if your wave function is normalized, fine, good enough. It is not normalized, then we will little bit change the definition. So if your wave function is not normalized, so I'll have to normalize it. Okay, so if I now find the expectation value of x, then this would be, you can write it as psi star x psi star dx divided by integration from minus infinite to plus infinite. I'll write minus infinite to plus infinite. I will write psi star psi dx. So this is how I would find the expectation value of position. Okay, so this is one of the important concept in the quantum mechanics. This is one of the important concept in the quantum mechanics. Okay. Let us say if I want to generalize this particular thing for an operator, so what I would do, so in general, you can take it as a moral of the story that we've done, that if you want to compute the expectation value of an observable let's say A, which is represented by, let's say, an operator A cap. Okay, we have to evaluate this thing. We have to evaluate this thing. If we don't know that whether psi is normalized or not, then you have to scale it using this. If it is normalized good enough, then this will give you 1. So it is the most general way of writing the expectation value of an operator A. So in the next lecture, we are going to continue with something called as the Ehrenfest theorem. Till then, take care. Try to revise all these concepts. I'll meet you tomorrow in a lecture called as the Ehrenfest theorem. Okay.